Before starting today's class, I will announce about the final exam. So actually, I plan to take the exam on the next week, the next class, but I changed the plan. So we will take the final exam the last day of this course. So it will be maybe. Okay, I will check the date. Okay, so the last day of this course is the June 14. Okay, right? So we will take the final exam on June 14. So during the regular class time. So actually, this final exam is the open book exam. So you can refer any material, but you cannot search you cannot use the electric devices, right? Because if you use the electric devices, then you can connect to the internet. So the internet is you can find anything from the internet. So you cannot use electric devices during the final exam, but you can refer any materials like some slide, lecture slide, or some textbook also. So you can. So this is the open book exam, okay? And then actually the final exam will cover everything we learned in this course. So such as the process architecture and the performance of the computer systems, then some issues on the semiconductor technology. So actually the final exam will cover everything we learned in this course. Okay. Okay. Any questions? And then the final exam will be the on-site exam. So which means that you need to show up on the exam day. So okay, so it's not online exam. So it's on-site exam. And then any questions? So also I will. I'm preparing for the last assignment for this course. So actually, the second assignment is for building Gen 5 simulator, and then you can configure the Gen 5 using some very simple process architecture, such as the CPU, and then simple cache and DRAM. And then in the last assignment, so you will be requested to run Gen 5 simulator with the system emulation mode. So and then you can change the configuration of the processor and then computer system using the Gen 5. And you can run several benchmarks like the spec 2017 benchmarks we used in the first assignment. So you will analyze you will be requested to analyze the characteristics of benchmarks with the Gen 5 simulator. Okay. This will be the last assignment of this course. So I told you about the final exam and then the last assignment. Any question? Okay. So in this time, I will cover the graphics processing unit because the GPUs are very popular nowadays. And then after today's class, so if we have time, then I will briefly explain about the domain-specific architectures, and then next two classes, I will cover the memory systems like the cache, virtual memory, and then some coherent. So if we have time, I will cover about the coherence and then consistency of memory systems. Okay, so actually, this is the advanced course of computer architecture field. So actually, the important topics in this course is to understand the detailed architecture of the modern processors, such as the out-of-order processing and then speculative execution, and then uh, some features of the modern computer systems. Okay, and then so as you know, so actually nowadays, so the academia or industry communities focus on some new architecture. They call the domain-specific architecture actually. So which means that, so actually in the first class, maybe the early classes, in the previous classes, I briefly explained about the semiconductor technology. So actually the performance of the processor can be advanced by the advanced in the semiconductor technology. So which means that if we can make the improved semiconductor devices, so which means that we can improve the performance of the normal processors. But nowadays it's very hard. So we can say that Moore's law is ending recently. So which means that it's very, very difficult to use advanced semiconductor devices on the processor design. So which means it's very hard. So so recently AMD and Intel, so it's very popular CPU vendors comparing to manufacturing their processors, but the performance of the single core is saturating recently, so which means that it's very hard to improve the performance of a processor. So actually, the desktop processor vendors such as Intel or AMD also try to increase the number of cores. Also, for the recent generation of the Intel CPU, Intel implement the little bit architecture, which means that Intel in this 12th generation CPU, so PP cores and WIMP cores are included. So it's kind of a big little architecture, similar to the ARM architecture. So actually, most of the effort to improve the performance of the processor is increasing the number of cores, then also improving some topologies or some the connections between multiple cores. Okay, so it means that it's not easy to improve the performance of the single core processor. So recently, many processor vendors focus on some different architecture of processor. GPUs is also, GPUs are very popular, which means that the price of the GPU is very expensive. This is because the GPUs are used for parallel applications. Okay, so it's like such as the neural network applications and then AI applications. So AI researchers think that GPUs are required. So GPUs are required device for AI research. So the architecture of the GPU is very different from the architecture of the modern processor we learned in this course, actually. So as I explained, the modern processors implement the out-of-order processing and speculative execution, also superscalar. So, but these architectural techniques require very complex hardware design, and then very hardware complex design also cause the high power consumption. Also, power is also a very critical cost in the process of design. So it's not easy to implement a very complex hardware or a very complex process architecture for some improve the processor. So, but the architecture of the GPU is very different. So actually, in the previous class, we learned about the vector processor, but the vector processor just handles the vector type data. And then the vector type data includes the multiple elements. So which means that multiple elements can be processed by single instruction. So this model is called the SIMD, single instruction multiple data. So recently this SIMD type architecture is good for the parallel processing applications such as the multimedia applications. So actually the AMD or Intel CPUs also support this SIMD instructions like the SSC, MMX, or ABX. But these instructions are developed for multimedia applications. Okay, and then if we use the SIMD architecture, then we just handle the vector type data. So we focus on the graphics processing unit. So the architecture of the graphics processing unit is very similar to the SIMD architecture, right? Because the graphics processor unit, these GPUs run multiple threads, but multiple threads share the same instruction. So if the multiple threads are executed, which means that these multiple threads handle the large amount of data in parallel. So GPUs are good for the parallel processing. So the architecture of the GPU is very similar to the SIMD architecture, but it's different also because GPUs focus on the thread execution. SIMD architecture just focuses on the vector type data processing. Okay, with a single instruction. So actually, I explained about something feature of the GPU in the previous class. Also, this is a very popular graph, which means so this looks like the Moore's law, but the performance of the typical processor is increased exponentially because of Moore's law, experiments the semiconductor technology, and also the efforts from computer architecture. The architectural mechanics also improve the performance of the single core processor. So the performance is improved by 52% per year. It's exponentially improved. So so recently it is the improvement rate is reduced in 2006. So like the improvement of the single core is saturated. But actually this graph is made by NVIDIA, so GPU manufacturer. NVIDIA advertised that with the GPU, then the performance can be improved. But this performance graph represents the performance of the single core processor. So CPU is not actually multi-core architecture, which means that the single core performance of the GPU is very low compared to the CPU. So it means that this graph is not correct, but the overall performance of the single GPU chip is higher than the performance of the CPU. But the design policy is different. It means that, so think about the out-of-order processing. So why do we use out-of-order? Why do we invent out-of-order processing? So with the out-of-order processing, we can increase instruction level parallelism. So which means that with the out-of-order processing, we can increase the number of instructions which are being executed in a processor. But GPU was some other parallel architecture. GPU exploits the thread level parallelism as I explained in the previous class. So GPU just focus on the many threads. So many threads are being executed inside of GPU. So actually the design policy is totally different. So it's true that GPUs are used for very high performance supercomputer systems because we use supercomputer for scientific or some level forecasting, scientific or economic applications. These applications are different from the normal applications, but actually these applications exploit the parallel processing, which means that GPU architecture is good for parallel processing. So that's why GPUs are used for supercomputer. And then when the GPUs are deployed in the supercomputer, then the performance can be improved. Okay, so you can say it's also about all the data in 2019. But we can find that 1, 2, 3, 4, 5. So 5 supercomputers out of 10 have 10 supercomputer. It gives GPUs. Okay, so let's see the GPU architecture. So actually the GPUs are designed for graphics applications. So which means that actually we use GPU cards to improve the performance of game application, right? Because so if we use GPUs, then we can enjoy the high quality 3D game. So this means that GPU has actually generated 3D processing. So which means that GPU generates 2D images, but the GPU calculate the depth of this object, and then GPUs generate the pixel data. So in display, so actually, I think everyone knows that the display is the image frames includes many pixels, and then many pixels also a single pixel includes the 3 color components. So which means that actually the GPUs need to generate these RGB values for each pixel, and then there are a large number of pixels in a single frame. So the original purpose of GPU is to generate this image frame very quickly. And then, so I will not explain some detailed image processing algorithm in this course because I don't know, but the image processing algorithms are actually the matrix, the linear algebra. So which means that we can represent these pixels like matrices, and then for the image processing, we just perform the matrix operations. So, and then the matrix operation like matrix multiplication, so we can implement the matrix multiplication with the parallel processing. So CPUs are designed for image processing or some video processing. GPUs are designed for accelerating this matrix parallel linear algebra, okay, like the matrix multiplication or matrix operations. Okay. So let's see some very basic Vertex pipeline. So this is the pipeline of the graphics processing. So the graphics processings are composed of Vertex processing, rasterization, and fragment processing, and the rest of operation. After these 4 steps, then we can generate the pixel data. Okay, so if you see that this object, so this is the some generated imagery, but if you see that this imagery, then you can find that these images are composed of many triangles. So this is the 3D, but we can represent this 3D image with the many triangles. So which means that actually the if we just if we can represent our normal image, our object with the many triangles, and then GPUs compute the data for each triangle. Okay? So actually, GPUs the Vertex processing, you can represent some normal object in the many triangles called the polygons. So in the Vertex processing, you can generate the polygon data, and then actually the data is equivalent from the pixel dimensions. So we need to represent the data inside of each polygon with the pixel data. So rasterization means that this triangle primitive can be represented using the pixel dimensions. Okay, so and then so we can represent the triangles like this pixel dimensions, and we need to generate the different depths or different pixel values of each polygon. So this fragment processing means that we can generate some depth, so we can generate the color data for each polygon, and then so we need to also decide the depth of the 3D image, which means that from the front of and back of the background object. So we need to decide the front object or background object in the polygon. So we need, which means that we need to combine the multiple polygons, and then based on some depth data of each polygon, we can generate the combined image. So when the multiple polygons are overlap, and then what depths of the multiple polygons are calculated, then GPUs can generate the final pixel data. Okay, so this is some original proposal of the GPU, and then for this operation, GPUs are designed for accelerating parallel processing of the pixel data. So this is the original GPU architecture. The GPUs are connected to the CPU via PCIe bus. So actually GPUs are co-processor. So which means that if there is no CPU, then we cannot run GPU because GPUs are co-processors. So actually GPUs are, so this is old architecture. So recently the GPUs are directly connected to the CPU, but in this old architecture, GPUs are connected to the CPU and those bridges. And then also you can find that those bridges are also connected to the system DRAM, so the memory. But recently, those bridge is included in the CPU chip. So actually, currently, the GPUs are also connected to CPU directly. It is because the GPU requires the very high bandwidth. Okay, no. So because the GPU is the co-processor, GPU requires the host interface, so which means that the GPU receives some commands or data from the host system. And then these GPUs are designed for implementing these graphics pipelining, like vertex processing, rasterization, fragment processing, raster operation. So So if you see that this GPU architecture, you can find that the GPU has many processing engines. Okay, because if you see that this image, that you can find that an object is composed of many polygons, and then based on the GPU Vertex pipelining, so we just focus on the computation on each polygon, right? So there are many polygons. So and then these computations are performed for each polygon. So this is very similar to the parallel processing, right? So not support the parallel processing for multiple polygon GPUs. GPUs have multiple processing engines here. So if the parallel processing are required, then GPU instructions are assigned to the multiple processing engine, and that is done by the multiple processing engine. Okay, and then for the rasterization, there is some pixel operation. So GPUs has the dedicated rasterization engine, and then fragment processing. Then we just focus on the each polygon data. So GPU actually has the texture in it. So GPU generate some different depths, different color inside of the polygon. Also, we can perform this operation using the parallel processing. So which means that the parallel processing engines inside of the GPU. And then rest operation. So if you use this GPU architecture, this GPU cores are connected to interconnection network. And then this interconnection network is connected to the rest operation engine and then L2 cache. So, and then also you can find that the rest operation engine or L2 cache is connected to multiple DRAM. So we need to store the frame data on this GPU memory. So this means that when the fragment processing is done, then this pixel data is given to the rest operation engine. And each pixel data is stored in the GPU memory, so DRAM. And then if this frame data is stored in the DRAM, and then actually the display engine displays store the data, read the pixel data from the GPU DRAM, and then represent some pixel data on the screen. So that's how GPUs work. So no, so actually, so recently GPUs are used for some parallel applications like neural networks or artificial intelligence applications. But actually, we can improve the quality of the 3D imaging or quality of the game application with GPUs. Which means that GPUs are originally designed for image processing or 3D processing or video processing. Okay? And then in order to accelerate this image processing, multiple polygons, GPUs have multiple processing engines. So which means GPUs are good for parallel processing operation. That's why recently we use GPU for general purpose parallel applications. Okay, but so I mentioned the general purpose. Oops. Okay, general purpose. For GPU's design policy, GPU is designed for actually graphics. So which means that inside of the GPU, you can find the many processing engines and then these PEs, they also use raster operation engines. But inside of the GPU, GPU architecture is designed for very regular data, which means that if we see some image processing data, so actually, the final result of the GPU is to generate this pixel data. So then there are many pixels in one frame. So think like the Full HD display is 2K, so 1K. So actually, the number of pixels is about 2 million. So it's a large number of pixels. But these pixels are regularly allocated in the memory. So which means that GPU's processing engines and the memory systems are designed for this regular data. But recently GPUs are used for general purpose applications. So which means that, so what does that mean? So general purpose application means that general purpose applications can handle random data or irregular data. And then the characteristics of these applications are very different from this image processing data or video processing data and game data. So there can be performance hurdle or performance bottleneck inside of the GPU. Okay. So think like so let's focus on the general purpose. Think like the CPU. Let's consider the CPU. The CPU is actually general purpose processor. Why? Right. So with the CPU, we can run any types of applications. Right. So actually the CPU. So the CPUs are designed for increasing instruction level terrorism, but which means that actually if we consider some many architectural techniques we learned in this course, CPUs are designed for some normal applications which have many control instructions, like branch instructions. So which means that the execution paths of these CPU applications are very diverse. And then CPU needs to support these diverse execution paths after the general purpose application. But GPU is different. So if think like this process engine. So I already explained that GPU's process engine or GPU architectures are designed for Vertex applications. The characterization of the characteristics of the Vertex applications are also very different from the normal application. So it means that Vertex applications just includes the many matrix operations, but we cannot find frequent control instructions inside of these Vertex applications. So which means that GPUs are not good for the normal applications which can be executed on the CPU. So which means if GPU applications include many control instructions like branch instructions, the performance will be extremely degraded. Okay? That's another performance hurdle of the GPU architecture. But also actually that is the performance hurdle of vector processor or array processors, like the processors that supports the SIMD instructions. Unlike the SIMD architectures, GPU supports the diverse executions. The feature intelligence can support the branch operations, but the efficiency is not good. Okay, that is another performance issues in GPU architecture. So the performance of the GPU is very high compared to the CPU, but GPUs are only good for the or certain types of applications, certain domains of applications. Okay, let's see the GPU execution model. So this slide shows the programming model of the different processor types. So we frequently use Python recently, but actually the default programming language for the architectural research or system research is C. So we usually I usually take the example from C. So for the sequential applications, like the normal application that runs on the CPU, so we frequently use the C. And then this high-level language like C is high-level language codes are compiled by compiler, and then the compiler generates the RISC type instruction. So the x86 is the CISC, but as I explained, inside of the CISC processors, complex instructions are coded into many RISC type simple instructions. So actually, the inside of the CPU is not different. Okay, so we can the RISC type processors can execute the many RISC type instructions serially. Okay, and then how about if the processor handles the parallel data, so which means the vector type data, then we can handle the vector type data, and then we can apply the CMD architecture. So, if we see some example of this sequential programming or sequential instruction, we can represent the instruction like this at x1, x2, x3. And then for the single type instructions, we can represent the instruction like the B add, B1, B2, B3. So only difference is that these single type processors handle the vector type instruction and the vector type data. And the vector type data includes the many elements. How about the GPU? So for GPU programming, we can use the CUDA-C developed by NVIDIA. So, and then if we just see the CUDA programming code, so actually as I mentioned, it's a CUDA-C. Actually, the structure of the program is very similar to C. That's why the GPUs are very popular recently, because the programming language is very similar to the C. But this CUDA code is translated, and these translated codes are assigned to the SIMT architecture. So then what is the SIMT, not SIMD? So SIMT is the single instruction multiple thread. So it's a thread, not data. So what does that mean? With the single type architecture, so we use the single instruction, and then with the single instruction, multiple data are used for processing. But the SIMT, we just use the separated thread. Okay, but these many threads are generated from the same code. Okay, that's why this architecture is called SIMT, the single instruction. So single instruction means that it's the same code, but from the same code, multiple threads are generated. Okay, that's why the GPUs are called SIMT. So NVIDIA advertised that their GPUs can execute 100 to 1,000 threads. So if you just see the Intel Xeon, so Xeon includes the tens of cores, like 32 cores, for example. And then if each core supports the hyper-threading, then we can run 64 threads concurrently. But NVIDIA advertises that their GPUs can run 1,000 threads. So we cannot compare the number of threads that can be run on the CPU and the GPU. The GPUs can run thousands of threads because GPU has the sync architecture, but either this sync architecture, what the many threads are generated from the same code. So which means if we just see the inside of the GPU's hardware architecture is very similar to the SIMD, right? So actually, GPU is the SIMD machine. It's wrapped by SIMD architecture. Okay, I explained it. So that's the RISC programming model CPU. So this program code shows the iterative loops of the CPU code. So we frequently use this type of code in our programs. And then if this code is translated to the assembly code, then we can know that. So we just translate this part with some kernel instructions. So actually, so when this code is translated, then the compiler just translated this kernel part with some instruction like add, and then the compiler generates some control instructions like branch instructions between add. So this is the kernel code for this iterative loops. So actually, this part is translated, and then there are several branch instructions after this kernel code. So that's how this RISC type programming languages are translated into assembly code. So if this code is executed, then you know that the same code is executed again and again, but we just change the control path using the branch instruction. So when the branch instruction is taken, then it goes to the first line of this kernel code again and again, and then after that, so we also find another branch instructions for the outer loop, and this branch instructions are also taken again and again. So actually, the processor, the process architecture looks like this. There is a register file, and then there is one AAU, and then so there is another register unit here, and then so the process just executes the operations instructions using the AAU and then register unit again and again, and then it's repeatedly executed. So which means that these instructions are actually inside of the processor. These instructions are repeatedly executed, but sequentially. Okay, that is the RISC type programming model. And then if we just apply the SIMD programming model, then there are multiple processing engines, and then also there are large, the wide register file. And then we can store each element of the vector type data on this wide register file. So like the B, add, B1, B2, B3. So this is the SIMD type model. So there are multiple processing engine, and the multiple processing engine just access the wide register file, and then also we can find the vector type register unit. The vector type register unit just access the global memory. And it's is just repeatedly also executed. So we can translate this inner loop of this example code to the vector operations. Okay. So if you see the translated code for the CMD that uses the CMD instructions, then you can find it. So as you can see, there is the outer loop here, and then you can find the corner code here. So what's the difference? So with this sequential programming model, the same codes are repeatedly executed. But with the if we use the CMD programming model, then we can use the vector type instructions or vector type registers, which means that we can translate this some repeated part inner loop to the vector type operations. Okay. And then in this example, the outer loop is not translated. So actually, this part is executed again and again. So which means that we can reduce the number of instructions for this repeated operate executions, but we just translate this inner loop to the using the CMD instructions. But the outer loop just execute the inner kernel again and again. Okay, so this is in the programming model, but in a GPU has somewhat different. So GPUs just where is the code? Oh, I cannot find here. I cannot find the GPU instruction. Oh, here. So this is some example code of the GPU. So if you see this code, then you can find some kernel instruction here. So then what is different? We cannot find any loop. So actually, if you see this code, then we can find that because of the inner loop and the outer loop and the inner loop, then the same kernel code is repeatedly executed. We can translate this inner loop with the vector type operations, the vector type instructions. But in the GPU just represent this kernel code using only this computation kernel, like here. And then you can find that the inner loop and outer loop structures are removed in the GPU. But then what is included? You can find indexes. So actually in the GPU programming model, we just assign the multiple thread. Okay, so if you use this code, we cannot find any repeated loop, iterative loop here. But instead, we can find that index. This program kernel just handles this already with the indexes. And then these indexes are computed from the GPU's own block index and thread indexes. Okay. So actually, these GPUs can identify multiple threads using block indexes and thread indexes. Right? And then GPU assigns these block indexes and thread indexes to each thread. And each thread just compute this basic computation part of the repetitive loop. Okay. So it's a little bit different. So actually, in the CPU model and that was in the SIMD model, actually if we find some basic computation kernel part, then actually the CPU programming model or SIMD type programming model just translate this part into the supported instructions here. But in a GPU, but we already know that we can parallelize this part, right? Because we cannot find any data dependencies between the different loops. So GPUs just remove the control part, iteration loop, and GPU generate the multiple thread, and then GPU identify is generate multiple thread with the block indexes and thread indexes, and then GPU using this multiple core, GPU just execute the basic computation. Okay. So that's how the GPU's programming model is a little bit different from the SIMD type or some normal GPU programming model. So it looks like, so actually, if we just see the CPU code, so it looks like the CPU serialized instructions. But in the GPU parallelized instructions into multiple threads. And then these multiple threads are executed again and again. So what is different? So difference is that actually CPU code iterator loop are removed. So you know, actually we can find any different kind of branching in CPU code. But you can also program the applications like CPU code, as I mentioned, we just use the many diversity the path using different type of branches and performance review, extremely iterating the review. Because as you can see, in GPU programming, then you recommend to remove some iterate loop or some other branch instructions. So if you stop GPU just the multiple key, but it's not recommended because the native of the GPU hardware. So if you see that inside of the GPU hardware like this, actually this execution model is very similar to the SIMD, right? It's the same. But so actually, so in this program model, this program is just translate the inner loop to the SIMD instructions. So that's why this SIMD processor have only 4 process engines and wide register 5. But as you can see, GPU's architecture looks like this, but no, GPU architecture. So as you can see, the GPU architecture is very similar to the SIMD architecture because the GPU has also wide register file and then also many processing engines. And then this we can read the required operands from the wide register file. But only difference is that the load store units are assigned to each thread respectively. So if you see the single type architecture, then you can find that there is the vector type load store units here. But this is just the programming model. It's somewhat different from the native GPU architecture, GPU hardware. But in the programming model, then individual load store units are assigned to the thread execution path. So also you can find the shared memory, but this shared memory is very similar to the scratch pad memory. So it's different, but the data can be shared by the multiple thread also, but it should be programmed by programmers. Okay, it's not the data are not shared automatically inside of the GPU. So you can find the global memory here. So actually the difference is that instead of vector type load store instructions, GPU's program model just has the independent load store units here. And then GPU just focused on the execution of the single thread. Okay. But this is just the programming model. So which means that actually inside of the GPU, the architecture is similar to the SIMD architecture. Okay. So it's like the illusion. So GPU provides the illusion to the programmer, which means that it looks like that the individual threads are independently executed inside of the GPU, but it's not true actually. Okay. So the difference is that GPU uses the thread, not the vector type data. And GPU has the shared memory, but I don't think this is some unique feature of the GPU. Okay? But also in the some programmers, GPU also provides the shared memory space. That okay, but it's not the it's not some representative feature of the GPU. Okay, so okay, then okay, so then I will explain how the threads are organized from the GPU computation kernel. So if you see some CUDA-C code, so you can find the .cu file. So which means that this is the CUDA-C file. Right? So but if you see some example code of the CUDA-C, then the CUDA kernel looks like this. So inside of the CUDA-C file, you can find the kernel name here, and then you can also find the dimension of this kernel, and then this is the argument. So actually, if you see the CUDA-C code, then you can find the kernels. Actually, these kernel parts are uploaded to the GPU hardware, and then actually only the kernel parts are executed inside of the GPU. So GPU just executes this part. So if you see the CUDA-C code, then in the kernel of the GPU looks like the function actually function of the normal C code. So which means that this kernel received some argument from the parent code, parent part, and then actually this data is transferred to the GPU memory, and then this data is executed by GPU hardware. Then how the threads are generated from a single kernel. So as you can see, you can find the kernel dimensions here. Actually, this is the kernel. And then inside of the kernel, the GPU generates the thread blocks. Okay, so thread blocks a thread block is a group of threads. Okay, the first, the GPU split the kernel into the multiple thread blocks. And then inside of these thread blocks, there are multiple threads. Okay, so for example, if we have 100 by 200 thread inside of the thread block, and then if the dimension of this thread blocks is like the 10 by 10, then the total number of threads are 10 multiplied 10 multiplied 100 multiplied by 200. Okay, so which means that inside of the GPU kernel, GPU generates the large number of threads, but GPU groups the multiple threads into the thread block, and that's so GPU organizes the thread blocks like this, and then each thread block includes the same number of threads. Okay, so it looks like this. So if you see that this kernel, so actually the first dimension represents the dimension of the thread block, and then the second dimension represents the dimension of thread inside of a thread block. Okay, so if you see that this code, this example, so you can find that the thread block dimension is the 2,1, so which means that there are two blocks, thread blocks, and then inside of a single thread block, this thread block includes 4 threads because the dimension is 4,1. So actually, if you see that this kernel generates the 8 threads. Okay. Then, so actually, this is how the thread blocks are assigned to the GPU hardware. So you can find that multiple thread blocks here. Then inside of the multiple thread block, there are multiple threads. So actually, GPU assigns the kernel code to the GPU hardware in the unit of thread block. Understand? So actually, GPU groups the multiple threads into a thread block, and then GPU assigns these multiple thread blocks to the GPU hardware, GPU core. So when these multiple thread blocks are assigned to the multiple hardware, then these threads can be executed in parallel because there are multiple hardware. And inside of this CPU core, that actually core means different. Actually, the NVIDIA core is different, but I just say that this is the CPU core, and then the multiple threads are assigned to the multiple processing engine like this. So these multiple threads are executed in parallel. Okay? Like this. So, so this is the SM called so SM means the streaming multiprocessor. So actually this is the NVIDIA terminology, not AMD, but we frequently use the SM, and we frequently use NVIDIA terminology because the GPU concepts are firstly developed by NVIDIA. So the SM is similar to the core of CPU. It's a little bit different. So actually, the NVIDIA advertised that NVIDIA GPU includes the maybe 800 cores. But this core of NVIDIA is similar to the actually ALU in the Intel CPU. It's very, very simple. So actually, GPU is a multiple and with 2.4, it's called 2.4 actually. So So there is the CUDA core. Actually, it's like the many hundreds CUDA cores, but this CUDA core is very similar to the integer plus floating point ALU. Okay, so when I mentioned a core, it's the stuff. So when NVIDIA mentions a core, it's very similar to the integer plus floating point ALU. So, and then inside of the GPU, so you can find that many processing engines inside of this some group of cores. So it's the same to the GPU. So in the NVIDIA GPU architecture, this single SM, so this single SM is very similar to the core of the CPU. So single SM includes the multiple CUDA cores, like this. So this is the SM, and then inside of the SM, there are multiple processing engines, like the, what happened? I don't know how to. So inside of SM, there are multiple CUDA cores like here. Like, so you can find the multiple CUDA cores here, and then the SM groups the multiple CUDA cores, and then so this is the SM. So in this example, there are 4 thread blocks, and then inside of the thread block, inside of a thread block, there are 8 threads. So in the NVIDIA GPU, we just assign the thread blocks to the SMs like this. So it looks like this. So in the GPU programming model, the thread blocks are assigned to the, it looks like it's a SM actually. So it's very similar to the core of the CPU. The thread blocks are assigned to the each SM, and then SM just execute the multiple thread inside of a thread block. Okay, so this is the execution model. So these are 4 thread blocks. Okay, and then you can, as you can see, there are 3 SMs, the streaming multiprocessors. So we assign the thread blocks to the multiple SMs, like 00 is assigned to the SM number 0, 1, 2. So 01 is assigned to the SM number 1, 0, 1, 0 is assigned to the SM number 2. And then because there are 3 SMs, we also need to assign thread block 1, 1 to the SM number 0. So it's like kind of a round robin fashion. And then, you know, inside of each thread block, there are multiple threads. So these multiple threads are executed by multiple CUDA cores, like multiple integer plus floating point ALUs. Okay, like this model. In this model, there are multiple actually ALUs, processing engines. So these multiple threads are executed in parallel. So this is the programming model of GPU. Okay, so I explained how the GPU codes are generated, and then how the GPU codes are assigned to the GPU hardware. And then actually, so let's take the 10-minute break, and then after that, I will explain about some detailed, not detailed, so brief architecture of the GPU. Okay, okay, let's take a 10-minute break. 오늘은 GPU까지만 해야겠네요. 뭐 사실은 이제 그 GPU 프로그래밍이나 이런 것들은 다음 학기도 이제 제가 대학원에서 이제 4번씩 가르치는데 4개 다른, 그러니까 2년 동안 이제
각 학기마다 이제 네 개 다른 주제로 이제 하게 되는데, 뭐, 제가 이제 GPU를 이제 좀, 이 시간에 브리플리 이제 설명하긴 하지만, 뭐, 다음 학기에 GPU랑 이제 GPU 프로그래밍 아주 간단한 그런 거를 이제 좀 가르치지 않을까, 그렇게 생각을 하고 있고요. 근데 이제, 과목이 겹치는 게 있어서, 그것을 정해야 되긴 한데, 어쨌든 다음 학기에 이제 좀 GPU랑 이제 GPU 프로그래밍에 대해서 이제 좀 더 디테일하게 이제 가르치려고 합니다. 뭐 말했듯이 이제 GPU라는 것이 요새 뭐 진짜 CPU만큼 사실은 CPU보다도 더 많이 틀리지 않겠죠. 어쨌든 비싸서 그런데 뭐 비싸기도 하고 파퓰러하기도 하고 뭐 그런 프로세서가 이제 되어버렸는데 그만큼 이제 중요하긴 한데 어쨌든 이제 GPU 구조라든지 이제 GPU의 성능이라든지 이런 부분들이 중요한 이제 프로세서가 되었고 중요하기 때문에 다음 학기 이제 가르칠 예정이고요. 아마 과목 이름은 아마 다를까 좀 이상할 겁니다. 겹치는 과목이 있어서 그래가지고 아마 과목 이름은 이상할 텐데 어쨌든 다음 학기는 이제 GPU를 계획을 하고 있어요. GPU를 계획을 하고 있는데 뭐 거의 이제 95% 정도 GPU가 될 것 같고 다음 학기 이제 토픽은 네, 사실은 그 한 학기에 이제 설명할 그런 내용인데 그러니까 지금 설명하는 그냥 인트로덕션적인 이제 설명이니까 깊이는 안 들어갑니다. 깊이는 안 들어가고 그냥 GPU가 이제 어떻게 됐다, 어떤 아키텍처를 가진다 정도 이제 좀 알아두면 좋아요. 이게 항상 이제 저는 이제 프로세스 아키텍처를 하는 사람이니까는 좀 항상 강조를 하는 게 우리가 이제 아키텍처 프로세서 구조를 이제 잘 알면은 사실 그 소프트웨어라든지 이런 성능을 끝까지 끌어낼 수가 있긴 하거든요. 근데 이제 CPU 같은 경우에는 이제 그 각각의 레이어가 굉장히 이제 많이 있고 앱스트랙션 레벨이 많이 있고 근데 각각마다 이제 최적화라든지 이런 것들이 참 오랜 역사에 걸쳐서 이제 이루어졌고 뭐 그렇기 때문에 사실은 CPU는 그냥 우리가 프로그램 짜면 알아서 잘 돌리겠거니 거의 이런 수준이 이제 되어버렸는데 GPU 같은 경우에는 프로세서 아키텍처가 CPU랑 또 완전히 다르고요. 또 GPU는 좀 CPU가 가지고 있지 않은 유니크한 컴포넌트들이 꽤 있습니다. 그런 거를 잘 이용을 하면은 성능을 이제 많이 높일 수 있는 그런 여지가 있는데 아직까지는 GPU는 이제 역사가 오래되지 않았기 때문에 이런 뭐 컴파일러 옵티마이제이션이나 이런 부분들이 그렇게 편하게 제공되지는 않아요. 물론 우리가 이제 프레임워크 써가지고 사실 뭐 머신러닝 어플리케이션을 짠다는 사람들도 프레임워크를 거의 의존을 하고 그 다음에 프레임워크 밑에서는 어떻게 돌아가는지는 잘 모르는 경우가 많이 있긴 한데 진짜 프로세스에서 어떻게 돌아가는지 근데 이제 GPU 같은 경우에는 실제로 이제 제공하는 뭐 프로세싱 엔진이라든지 아니면 뭐 메모리라든지 이런 것들이 다 CPU랑은 다르게 어떤 목적에 따라서 다 나눠져 있기 때문에 뭐 실제 굉장히 이제 밑으로 내려가서 프레임워크 아니고 프레임워크 밑으로 내려가서 이제 프로그래밍을 할 때 이제 GPU 구조를 잘 알고 있으면은 어느 정도 또 퍼포먼스 옵티마이제이션을 뭐 할 수가 있습니다. 그래서 사실 GPU 같은 경우에는 아키텍처를 이제 잘 아는 것이 약간 이제 소프트웨어 성능이라든지 이런 데 굉장히 중요하고요. 네, 그래서 그걸 좀 다음 학기는 이제 그 포커스를 둬서 이제 강의를 하려고 합니다. 오케이. So okay, so now I will explain about the GPU architecture, GPU hardware architecture. So actually, I explain about some execution model of the GPU. So actually, this execution model explains how the multiple kernels are generated from a single, multiple threads are generated from a single kernel, and how the generated threads are assigned to the GPU hardware. So this is some execution model. So actually, these execution models are exposed to the software. So this means that when you generate the GPU kernel like this, so you need to decide the block dimension and the thread dimension in a block like this. So actually, the programmer decides the dimension of the block and dimension of the thread. So actually, the maximum dimension of the thread block and the maximum dimension of the threads in a block are determined by GPU hardware specification. Sometimes these numbers are determined by the limitation of the supported dimensions for thread blocks and the thread dimensions. Okay, so let's see the inside of the GPU architecture. So why is it called the GPU? So you can find double GPs. So actually, the first GP of the GPU means the general purpose. So as I explained, the GPUs are originally designed for the graphics applications. So recently, the GPUs are used for running general purpose applications, especially neural networks or machine learning applications. So general purpose GPU means the GPU plus programmability, which means that like the CPU programming, then we can program the GPU code with the CUDA-C or OpenCL, another framework. So we can program the GPU code, and we can run the GPU applications on the GPU. So which means that the GPUs provide the programmability, and then using the provided programming framework, we can generate any types of applications. Performance is not guaranteed because of some control paths and then because of the native architecture of the GPU. But with this GPU programming framework, we can generate any types of application, GPU application. So that's why it's called the GPU. It's a general purpose graphics processing unit. So we can program the GPU application using CUDA-C or OpenCL. So usually the NVIDIA supports the CUDA, and then OpenCL is supported by AMD. So AMD also builds the GPU card. Discrete GPUs. Also, recently the Intel plans to actually the Intel already have the discrete GPUs, and then Intel also used the discrete GPUs on the data center system, and then recently the Intel also plan to sell discrete GPUs to the customers. Okay, so actually OpenCL is supported by AMD and then Intel. So as you can see, the OpenCL is some generic language that supports some domain-specific processors such as the GPUs, also FPGA. So actually, OpenCLs are developed for heterogeneous computing. Okay, but for the GPU programming, so we frequently use the NVIDIA GPU. So that's why the CUDA is more popular than the OpenCL for GPU programming. So we use the CUDA-C, and then also CUDA also supports the OpenCL. But if we use the NVIDIA GPU hardware, then we can use the only CUDA. Okay. So the problem is that if we just write the CPU program code, so actually most of the CPU is different. The ARM is the different, but if we write some x86 programs, like so, which means that the applications that support the x86 ISR, then we can just write the high-level high-level code using the x86, high-level code using the any programming languages, and then these high-level codes are translated into the assembly code, and then this assembly code is also translated into x86 machine instructions. And then, how about the GPU? So in order to support the programmability on GPU, then which means that NVIDIA or AMD GPUs need to open the supported instructions, which means that ISA, instruction set architecture for NVIDIA GPUs or AMDs. But also it's the same to the Intel CPUs, but by generations, NVIDIA changed their instruction set architectures, so it's supported ISA, so which means that actually these native instructions can be supported by programmer inside of the Q.C, but sometimes so actually the GPUs are developed very quickly. So GPUs has some many generations, and then each generation supports its native instructions. So which means that it looks like that it's very similar to the new instructions are included in the new generations of NVIDIA GPU. So which means actually in order to support the newer hardware, the newer GPUs, we need to install the newer version of CUDA. And then also another problem is that sometimes newer version of CUDA does not support the old generation GPU. For example, CUDA, so the recent CUDA does not support the Fermi architecture. So it's very old architecture of the NVIDIA GPU. So sometimes the backward compatibility is not maintained by this NVIDIA GPU. Okay, the GPU. Okay, so it's a little bit different, but this is because the GPUs are the history of the GPU is a little is shorter than the history of the CPU. So actually, it's not stabilized. The instruction set architecture is not stabilized. Then also the backward compatibility is not supported by your CUDA version. Okay. So we can use the CUDA or OpenCL for GPU programming. So let's see the inside of the GPU hardware. So as I mentioned, GPU is composed of, so I will use the NVIDIA terminology, not AMD. So AMD terminology is a little bit different from the NVIDIA terminology, but the basic GPU architecture is very similar. So you can understand the basic GPU architecture using the NVIDIA terminology. So this is some brief architecture of the GPU, overall architecture of the GPU. So inside of the single GPU chip, there are multiple streaming multiprocessors. So as I mentioned, this streaming multiprocessor is the concept of the streaming multiprocessor is similar to the core of CPUs. So there are tens of, so like the 15 or 30, so there are tens of streaming multiprocessors inside of a single GPU chip. So if you see the inside of this SM, so single streaming multiprocessor, so you can find the required hardware modules for executing instructions. So this architecture, if you see the name of the hardware component like this, so you can find this component name is very similar. So it's similar to the component of CPUs. So there is instruction fetch engine, then is warp scaler. So it's a little bit different. And then also you can find the scoreboard and then issue engines. So similar to the out-of-order processor. the Thomas Blow algorithm. Also, you can find the SP. So this is the CUDA cores. So SP means the streaming processor. And then SFU is the special function unit. So actually GPU needs to support the special functions such as the square root, cosine, and sine functions. So in order to support these functions, GPU has the dedicated special function units and then load store units. So if you see the architecture of in architecture of the single streaming multiprocessor, so it's similar to the pipeline architecture, like this is the integer ALU, and this is the load store unit, and then it's a floating point unit. Right. So, but the different is the if you can find the different components, which is the warp scheduler. Scoreboard, you can find the scoreboard or issue engine also in the outer board plus the Intel CPU, like the normal CPU architecture. So you can find the register file, but the architecture of the register file is a little bit different from the CPU register file. Okay, and then also you can find the local caches, like, and then as I mentioned, the GPU supports the multiple different memory spaces, and then each local cache supports these multiple different memory spaces. So there are three different kinds of local caches, like the constant cache, hexacache cache, and then data cache. So you can find the shared memory here. The shared memory is very similar to the scratch pad memory. And then actually the scratch pad memories are shared by multiple threads inside of the same thread block. And then actually the contents of the shared memories are managed by programmers by instruction, right? So actually these different type of cache memories are managed by hardware. So there are constant caches, extra caches, and data caches. So constant, actually GPU handles the different kinds of data, constant data or parameters. This data is stored in the constant cache. Also, as you in the native, not to support the native graphics pipelining, so you can find the texture in here. So this texture data is stored in the texture cache. Then this data cache is similar to the data cache of CPUs. Also, there are multiple streaming multiprocessors, and then as you can see, so the main memory of this GPU board is a little bit different from the main memory of a CPU, which means that if we see the normal computer systems, then you can find that there is CPU here, and then the CPU chip is connected to the memory DIMMs, like DRAM DIMMs, and then we can attach the DRAM DIMMs on these DIMM slots. So these are connected to the memory controller of the CPU. Okay, but GPU, we cannot change the DRAM chips like DRAM DIMMs inside of the GPU board. So actually, as you can see, these DRAM chips are soldered on the GPU PCB. So which means that GPU has the multiple memory controllers, and then these multiple memory controllers directly access the multiple GDDR chips. Okay, and then these multiple DRAM chips are partitioned into multiple memory partitions, and then actually CPU has the shared architecture, and then these shared architectures can be shared by multiple streaming multiprocessors. So it's like the shared last level cache in CPU processing. But the memory part partitioned into shared cache, then after that, there is some dedicated memory controller for the partition memory chips, and then memory controller directly access the DDR chip. And then these multiple memory partitions are connected via interconnection networks. So in a single GPU chip, there are multiple stream multiprocessors, and then there are multiple memory partitions, and then these multiple SRAMs and the memory partitions are connected via interconnection network. Okay. So, and then the unique feature of the GPU is that it's warp scalar, and then I will explain about the warp later. So as we can see in the example GPU kernel code in the previous slide, GPU kernel has the dimension of grid is the dimension of the block, and then dim block. So this is the dimension of the thread inside of a thread block. So and the GPU kernel is called this based on these dimensions. The GPUs organize the thread blocks and then the thread inside of a thread block. And then these thread blocks are called CTA. This is also NVIDIA terminology. But the CTA means the cooperative thread arrays. So actually this is the thread blocks. So based on the dimension of the thread blocks, the dimension of the grid, the multiple CPAs are generated from a single kernel. So there can be multiple kernels also inside of the CUDA core. So it looks like the function of the normal CPU code. So there can be multiple kernels, and then actually the kernels are executed by GPU. Okay. So when the kernel is launched by the kernel can be launched by CPU. So if a kernel is launched, then multiple CPAs are generated from the single kernel. Okay, like this. And then these multiple threads. So actually, each thread also includes the each CPA. Sorry, did I mention CPAs? The multiple CPAs are generated from the single kernel. Okay, and then in each CPA there are multiple threads like this. So so this number of threads are determined by dim block. So this besides the number of threads inside of a CPA. So this is so these threads are executed inside of the GPU hardware. And then this is the software model. So actually the software programmers needs to decide the dim grid and dim block, so dimension of the grid and the dimension of the block, and then when the kernel is designed. But so you need to focus on the warp here. So warp is also the NVIDIA terminology. So actually I said that so GPU supports the DIMT. So which means that multiple threads can be executed independently. But this is also single instruction. So which means that like this soft model, the multiple threads are generated from the single kernel. Okay, so which means that the same code, same instructions are shared by multiple threads. And then in the software view, these multiple threads are executed independently inside of the GPU. But if these multiple threads are independently, like the hundreds of threads, if hundreds of threads are independently executed inside of the hardware, then efficiency will be very low, right? Think like this. So it's a think like the Xeon core. So the Xeon core can support the 64 thread. concurrent thread. So let's also assume that these 64 threads are independently executed inside of this Xeon chip. So you know the Xeon is composed of very PP cores, it's a high performance core. So it will be very fast, but actually if the hundreds of threads are executed inside the processor, then the performance may be very low because it will be very inefficient. So actually, we need to focus on the single instruction. So which means that even though these multiple threads are executed, these multiple threads share the same instruction. Right? What does that mean? So actually, this is the same instruction code, and then multiple threads share the same program counter because it's the same instruction. So in order to increase the performance, we can execute the multiple instructions in parallel. It's like the SIMD. Right. What is the benefit of the SIMD? So SIMD means a single instruction, multiple data, and then as you like the vector instructions. So multiple elements from a vector data are loaded from the register file in parallel, and then these data are executed by the same instruction using the ALU, and then actually at the same clock, the results are generated. So this is the SIMD architecture, and then SIMD architecture is actually good if the code structure is very simple. Which means that there is no branch instructions and there is no control instructions inside of the SIMD type instructions. So with the SIMD type instruction, then we can increase the efficiency of parallel processing. So GPU is a SIMT, but GPU also designed for accelerating parallel processing. And then many threads, so these multiple threads share the same instruction, which means that we can design GPU hardware like SIMD architecture. In order to execute the multiple instructions, and then these multiple instructions will have the same multiple thread. In order to execute the multiple threads in parallel, and then if these multiple threads have share the same instruction, and then we can execute these multiple threads like SIMD. Okay. So in order to increase the efficiency of the processing, GPU groups the multiple thread into warp. Okay. So in an NVIDIA GPU groups the 32 thread which share the same instruction. Actually, as you can see, these threads are generated from the single core, just the same core, same kernel, sorry. Right. So which means that actually these threads share the same instruction. So which means that we can group the multiple threads which are generated from the same kernel. So it is same, which means they should share the same instruction, which means also share the same program counter. And then so group the multiple threads into a warp, and then NVIDIA GPU execute this warp like the in the architecture. So think like this. The instruction for this warp, the instruction is the same. It's a single instruction. Even though the threads, there are multiple threads, then because the instruction is the same, then we can process these instructions like the SIMD, the multiple data are accessed. Okay, that's how the GPUs handle the parallel processing. The thread group called a warp. Okay, so this is the warp is the basic execution unit, the basic unit for execution in a GPU. So which means that threads are grouped into a warp, 32 threads are grouped into a warp, and then at every cycle, this warp is issued to the execution engines, and then multiple threads are executed in parallel by this execution engine. So if you see the GPU, inside of the GPU, the SP, the number of SP is usually same to the number of threads in a warp, like 32 SPs. So which means that in one clock, we can issue a single warp every clock. Okay. But the warp is not revealed to the software engineers. So this is some hardware architecture of GPUs. So actually, this software engineer just to know that, oh, there are multiple threads in a CPA, but inside of the GPU hardware, these multiple threads are grouped into a warp, and then actually the GPUs execute the multiple warps. So that's why there is a warp scheduler inside of a SM. Okay, so a warp scheduler just decide which warp will be issued to this processing engines. Okay, so this figure shows the architecture of the NVIDIA Fermi architecture. So as you can see, oh, it's so small here, but you can see there is an instruction cache like in the normal CPU. The instruction memory is here, and then there are two warp schedulers. So multiple threads are grouped into warp, and then these warps are assigned to the GPU hardware. Also, the GPU hardware can handle the limited number of warps. Actually, the NVIDIA Fermi architecture can handle 48 concurrent warps. So which means that, and then each warp can include the 30 thread. So this is the maximum number of threads that can be handled by one SM. Okay. So when the threads are launched, so kernels are launched on the GPU, and then as I mentioned, what happened? As I mentioned, the kernels is grouped into thread block or CTA, and then the CTAs are assigned to SM. And then inside of a CTA, we can find many threads, and then many threads are grouped into warps. And then warps are scheduled to the processing engines or CUDA cores. Also, there are two warp schedulers, so which means that this Fermi architecture can issue maximum two warps per cycle. Okay, and then these warps are executed by the multiple cores. So you can find the 16 cores here, or another 16 cores here. And because there are two warp schedulers, one warp can be assigned to this cores, and then another warp can be assigned to this core. 16, right? Right. So you can find the load store units and then special function units here. Okay. And then another feature of the GPU is that GPU has large unified register file. So GPU is the same team model, so which means that every thread can have registers. Okay. So in the Fermi architecture, there are 48 concurrent. A single SM can support up to 48 concurrent warps, and then each warp can include the 32 threads, so you can calculate the number of supported threads inside of a SM. So there can maybe thousand, like maybe it's similar to the 1500 thread inside. So each thread will have the registers. So think like that. If each thread has the authority registers, and we need to assign the large registers to support the large number of threads. And then, like that. So actually, a single SM has the it's large also, very large register file, but this register file is the unified register file. So which means that, so actually the maximum number of registers supported by a single thread is defined in GPU ISR. Okay, so actually the single thread can have up to 256 registers in an NVIDIA GPU, but it depends on the size of the kernel. So which means that, so actually this kernel is computed by GPU. So which means that a certain kernel size is very small, a certain kernel may require small number of registers, or the size of a certain kernel is very large, and then this kernel may require a large number of registers. So actually the required number of registers can vary by different kernels. So actually the required number of the registers per thread are decided when this kernel is compiled by to the compiler. Okay? And then the compiler has just assign the required size of registers in this unified register file of the GPU, and then assign some part of this unified register file to the thread of this kernel. Okay. So another feature of this GPU is that actually the register file size of this SM is larger than the size of the data cache. Okay, it's interesting. The GPU supports the very large register file because not support the large number of threads. So also you can find this shared memory and the add-on cache. And another feature of the GPU is that GPU supports the unified shared memory and add-on data cache, which means that the programmers can adjust the size of the shared memory and the add-on cache. Okay, so this is the hardware, so the maximum size is the 64 kilobytes. But you can adjust the size of the shared memory and add-on cache, add-on data cache, like the 32 kilobyte of the shared memory and then 32 kilobyte of the add-on data cache, or 48 kilobyte of the shared memory, or 16 kilobyte of the add-on cache. So we can adjust the size of the add-on data cache, and then the programmers can decide the size of the cache or shared memory. So this is the Fermi architecture. And then in the Kepler, so it's a little bit different. So it's a very small here. So in the Kepler, the SM is called the XMX. So if X is added, so which means that this is the extended. So in the Kepler architecture, the Kepler architecture can support up to 4 warps. Okay, so there are 4 warp schedulers, so which means that one SM can issue 4 warps every cycle. Okay, also which means that, so it looks like that the 2 SMs are combined, and then in the Kepler architecture. So the 2 SMs of the Fermi architectures are combined, and then the NVIDIA builder define the SMX, and then this one SMX supposed to have the one SMX has 4 warp schedulers, and then you can increase the number of warps that can be issued every cycle. Okay, but the basic architecture is very similar to the interferometry architecture. And the Maxwell, and then in the Maxwell architecture, actually, if you see this Kepler architecture, there are multiple warp schedulers, and then SPs. So this means that processing engines are shared by 4 warp schedulers. Okay, so which means that if these cores are not used, then warp scheduler can issue any warp to the available core. Okay, but in the Maxwell architecture, the processing cores are isolated, and then each processing cores are assigned to the single warp scheduler. Just so which means that the warp schedulers and then computer cores are isolated. Okay. So and then Pascal is a Pascal, and then so another feature is that actually these 4 SMs, actually 2 warp schedulers share where is the register file? Oh, so register files are also isolated in the Maxwell. Okay, so and then in the Pascal, so it's really same actually. Okay, and then Volta. So it's a recent architecture, and as you can see, in the Volta architecture, is also the warp schedulers and then processing engines are separated, isolated, but the tensor cores are included not to support the matrix instruction. Okay, so because of the neural network applications, the NVIDIA also include tensor cores, and then these tensor cores execute the matrix instructions. Okay. So by generation, the GPU architectures are changed, and then as you can see in the Fermi architecture, then there are two warp schedulers, and then these 2 warp schedulers share the same the multiple processing cores. And then in the Kepler architecture, the number of warp schedulers are increased, and then also the number of cores are increased. And then these multiple cores are shared by multiple warp schedulers. And then the Maxwell, the warp schedulers, and then register files, and then processing cores are isolated. So by generation, the NVIDIA changed the architecture of the GPU. So we can analyze some pros and cons of these architectures, but sometimes actually so these architectures are changed by the characteristics of popular applications actually. So why the tensor cores are included? So in order to support the neural network, in order to accelerate the neural network applications. So which means that if characteristics of the supported applications are changed, then also the architectures can be changed to accelerate some specific execution or specific operations required by applications. Okay, register file. So as I mentioned, the GPU has the large unified register file. So actually, but GPU also needs to support the wide data. How can I? Multiple data read from the register file, like the SIMD architecture. Okay, so as I explained about the SIMD architecture, The simple architecture is the wide register file, and then in this wide register file, each element can be read from this wide register file in parallel. GPU has the unified register file, but GPU works like the SIMD architecture. That's why GPU supports the warp. Okay, so when a single warp is executed, and then a single warp includes the 32 thread, and then the 32 thread need to execute the same instruction. So which means that 32 instructions needs to read the different 32 operands from register file, right? So in order to support the parallel access is in the unified register file. The GPU register files are composed of multiple banks. And then, so for each lane of the register, multiple banks, then the GPUs can, the warp schedulers can read the operands from the register file, like here. So you can find the multiple lanes in the register file here, and via these multiple lanes, the warps can read the multiple data from the register file concurrently. Also GPU, so I mentioned that GPU register file is the unified register file, so which means that compilers can assign the required part in the register file. Okay, so actually GPUs has the hardware component called the operand collector. So it is because the data assignment in the register file is the programmable, which means the assignment of the data on the register file is determined by compiler, but it's programmable. Okay, so GPU does support the large unified register file. So which means that when some instructions are executed, like add R1, R2, R3. So if this example instruction is executed, then the location of the R2 or R3s are different by kernels. So which means that we need to translate the R2 to the actual address in the register file. So GPU has the operand collector. The operand collector translates this register number into the address of in the register file, and then actually the operand collector reads the multiple operands from the register file, and then just deliver the read data to the execution engines. Okay, so which means CPU requires the operand collector. Okay, and then if the required data are ready by operand collectors, then instructions can be executed by to the core engine. Then it's written back to the register file. Okay, it's a very simple pipeline architecture, right? And then actually the GPU does not support the out-of-order processing. Okay, so the instructions are executed in order. And question: how can we improve the performance? So the problem is that GPU does not support out-of-order processing. So then, because of the hazard, like low hazard, the true hazard, then performance can be degraded. Then how can we increase the performance? How does GPU handle this situation, like low hazard? Think like this. So when a warp is issued to the when a warp is issued, then it will take time until the write back. Okay, because this processing engine is the pipeline, and then the latency of this CUDA core is larger than 1, actually. Think like the integer or floating point AL. Floating point A, the latency of the floating point AL is something like 4 or 5 or 8 for the very complex floating point operations. So actually, because of the low hazard, there can be many empty slots. So how can you solve this performance issue? So as I mentioned, the Fermi architecture supports the 48 up to 48 concurrent warps. But you know, the number of keys, there are 2 warp schedulers, then also keys. Actually, there are 32 CUDA cores. Then how can we increase the how can we handle this low hazard issues? So performance drops by data dependency. The hint is there are 48 warps. Multi-threading. What is multi-threading? So actually the GPU hardware supports the fine-grained multi-threading, so which means that the fine-grained multi-threading means that at every cycle, the executed threads are changed. So for example, in a CPU domain, if a CPU just supports the fine-grained multi-threading for the 4 thread, like thread number 1, 1, 2, 3, 4, then at every cycle, the CPUs change the activated thread. So the clock cycle number 0, then 1 is executed, and then 2 is executed, 3 is executed, 4 is executed, and then 1 is executed, 2 is executed again and again. So this is the fine-grained multi-threading. The GPU has, so in the Fermi architecture, actually the recent architecture support up to 32 warps. But in the Fermi architecture, the maximum concurrent warps is 48. The number of maximum concurrent warps is the 48. So there are multiple warps. So actually the GPU's hardware is the in-order processor. It's very simple. So in order to avoid performance drop by data hazard or the data dependency, GPUs support fine-grained multi-threading. So which means that at every cycle, the GPUs change the activated warps. Okay. So for example, clock number 0, warp number 0 is executed, then 2 is executed, and 4 is executed, blah blah blah. Like this. Okay. So, and then as I mentioned, the GPU, the registers of some kernel can be assigned to the unified register file, so like this. So actually in order to support the SIMD-like processing, the GPU register file is composed of multiple banks, and then each thread of these different register numbers are assigned to the different lanes, okay, different banks. So actually we can assign the registers of different warps like this. For the warp 0, the register number 0 to 7 are assigned to this lanes 0 to 31 and for 32 threads. Okay, and then for the warp 1, we can assign the different part of the unified register file for the different warp like this. So as I mentioned, GPU has the operand collector, and operand collector translates translate the register numbers, and then based on the thread warp numbers, and then thread IDs, thread numbers. Okay. Okay. So. Okay, I will quickly explain. I'll quickly explain. So let's think about the register unit of the GPU. So if you see this processing engines of the GPU hardware, you can find the multiple processing engines. Also, you can find the multiple load store units. But problem is that actually think like the cache. So usually the cache has only one read-write port, right? If the cache has multiple ports, then cache size will be very increased, right? The port is the hardware resources. So if we increase the number of ports in the memory component, then the size of this memory component is also increased. So actually the size of the memory, it depends on some technology, but if we use the 2 ports, then the size is nearly double. Not nearly, not double, but it's about 1.5 times of the single port memory. So the problem is that with the multiple processing engines or CUDA cores, we can execute the multiple thread, like thread in a warp concurrently. But memory is different. So actually the cache has only single port for the read and write. So actually, which means that there are 32 threads inside of a warp, and then the load or store instructions are issued for this warp. Then this 32 thread can generate up to 32 address requests. Okay, right? There are 32 threads in a warp, and then GPU execute instruction, using a warp unit. So if a single warp is executed, execute a load or store instruction, then 32 memory requests can be generated. What does that mean? 32 requests are enqueued in the request queue before the register file, and then the register file needs to handle this 32 requests one by one, okay, sequentially. The problem is that processing part can be executed in parallel, but because of the limited resources in the memory component, memory requests should be serialized in the load store unit. So which means that if a GPU thread executes the load store instructions, then it will take longer time to serialize. The benefit of the GPU is the parallel execution. But if the load instruction is executed or store instruction is executed, then processing for these instructions should be serialized. So it's also significant performance issues. So in order to avoid this case, GPU support the memory coalescing. So if you see the pipeline of this load store unit, then you can find some pipelines in the load store unit here. Then warp is executed, and then operand collector collects the required operand from the register file, and then address is generated for each thread. And then you can find another pipeline here. So memory coalescer. So memory coalescing means that okay. So if the address of the request address for this thread can be merged in one cache line request. So for example, this thread requests the data from the 0x00 and the 4 byte, and then this thread requires the data from the 0x01, and then it's 04, the 4 byte, and 0x08, 4 byte, the next thread. So which means that we can merge this request into the very large one request. So for example, if the cache line size is large, like 128 bytes, then we can merge the multiple requests from the multiple thread into the one cache line request. And this processing is called the memory coalescing. And the benefit of the memory coalescing is that even though the first thread executes a multiple load instruction, but only one or two cache requests are generated. So which means that the multiple requests are merged into a small number of requests. So this is the memory coalescing. But this memory coalescing is only effective for regular data accesses, like the image processing or some multimedia application, observed in image processing or multimedia applications. Right. So if we just handle the multimedia data, then this multimedia data is aligned in the memory space. But for the general purpose application, the memory access patterns can be diverse. Which means that the irregular memory access patterns can be observed. So in this case, when the request, even though the requests are coalesced, this coalesced request, the number of generated requests will be larger than the 1 or 2. So which means that in a single warp, many big memory requests can be generated. Okay. The memory addresses from a single warp is not coalesced. Okay. And then it's very critical for the GPU performance, right? So actually, which means actually the GPU is designed for Vertex applications. So actually, CPU supports the memory coalescing to reduce the number of requests from a single warp. But if the general purpose applications are executed, and then the general purpose applications exhibit the uncoalesced memory request like this, then a single warp will generate many memory requests. And then this is the significant performance burdens in a GPU. Okay, this is another some research topic in the GPU architecture. Okay, so I will stop here. I cannot complete the GPU part. Okay, so I will stop here and then. Okay, so I will explain about some memory systems in the next class. Okay, any questions? Okay. So thank you for your attention, and then see you in the next class. Thank you, guys.